1. Okay, so welcome to Math341. This is lecture 12. I want to talk a little bit about coding, and then I want to start talking about one of the most useful techniques in all of probability, differentiating identities. This class does not have real analysis as a prerequisite. If you would like to learn real analysis between now and say 15 minutes from now, that would be wonderful. And then we can justify some of the stuff we're going to do. Otherwise, we will just assume that certain operations are justified and go with it. In some situations, we can actually justify it. Whenever we're dealing with finite sums, we can always justify interchanging the derivative and the sum. But whenever you have an infinity, you have to be careful. And I might just give one or two examples to just demonstrate how careful you have to be. All right, so we'll talk about coding, we'll talk about differentiating identities. And whenever you see an idea, you always want to ask, what is it good for? And one of the things differentiating identities is good for is computing moments. In particular, computing the means, computing the variances. So if the mean is 0, then the variance is just the second moment. If the mean is not 0, the variance is the second moment minus the square of the first. So if we can calculate moments, we can calculate means and variances. These are the two most important ones to be able to compute. The general takeaway from all of this is if you are ever successful in life and do something, milk it for all it's worth, right? It takes a while to do anything. Once you have it, what else can I do with it? It is a lot of work to prove an identity in mathematics. Once we have that identity, it's great if we can generate new identities from it. And that's one of the key ideas in differentiating identities, taking one identity and creating an infinite family of identities from that. Okay, so, going back to the crackerjack problem, I've just posted my code, so it's now on the slides. You can take a look at this. I strongly urge you to write your own code to investigate a problem like this. For this code, the way I was doing it was what I talked about in class, that as soon as we find a new toy, I will just change my numbering. So that's the lowest number that's missed. And so, because we only care about have we seen a new toy or not, we can always just keep dynamically changing the labels. And this just makes it a little bit easier to write the coding. I don't have to worry about checking to see, is this something new? And then updating my list and whatnot. I can just keep track of what is the number of distinct prizes I've seen. And so if I've seen 4 distinct prizes, and there's 10 possibilities, if I choose a number between 1 and 4, that's a prize I've already seen. If I choose a number between 5 and 10, that's a new prize. So if I choose 8, I will just call that my next new prize, and I've now seen 5 prizes. All right, so this is the code to calculate that. And what's nice is we can keep running sums for the first and the second moments, and then just divide by the number of iterations and just compute these without storing anything. If you want to store 1,000,000 items, if you want to store 1,000,000,000 items, that's going to take up space. In a lot of programs like Mathematica, it's going to really slow it down if it has to store all of that. And so you want to think about how much data do you want to save. It's nice if you have some of that data, but it's going to slow it down. And so I then ran a bunch of simulations of 10 prizes and 1,000 prizes, doing various numbers and recording how long it took. And one of the things that's nice to see is that when I went from 100,000 runs to 1,000,000 runs, I increased things by a factor of 10, and it took about 10 times as long. When I went from 1,000 to 10,000 with 1,000 prizes, it wasn't quite a factor of 10, but it was ballpark, something like that. And again, this is not going to be a perfect factor of 10 because my computer is doing other things at the same time. But over a long period of time, if I really run the programs, it should be about a factor of 10 because you expect it to be linear. If you're storing things, it's no longer linear and things become a lot worse. And so you can see that the predicted mean and the predicted standard deviation are very close to what we're getting experimentally. It's not a proof that we haven't done a mistake, but it is strong evidence that we are looking at this problem the right way if we're able to come up with such a great prediction of the mean and the standard deviation. Okay, This is a slight modification of the crackerjack code, so I'm calling it array crackerjack, because what I'm going to do now is, rather than just keeping track of how long it took, I'm going to store the number of times it took that amount in an array. So for instance, if I have 1,000,000 trials, I'm not going to store things into a list of length 1,000,000. I'm going to store how many times did it take exactly 1 box, exactly 2 boxes, exactly 3 boxes, exactly 4 boxes. I'm just going to have counters. Now, the problem is I could be extremely unlucky. If I have 2 prizes, is it possible it could take me 1,000 tries before I get both prizes? Yes. Unlikely, but yes. Could it take 1,000,000? Yes, but unlikely. So if you notice in the code, which I know you're looking at extremely carefully right now in real time, there's one part over here where, if count is less than twice the number of prizes squared, then I'm going to increase the corresponding array by 1. We expect that it takes, if there's t prizes, t log t is the expected number of boxes we need to get all the toys. So I'm going up to t squared times 2. But it's possible I might have been extremely unlucky and it might have taken more than that. And so if it takes more than that, what do I do in that case? So this is an if then else. So if this condition is true, then I'm going to increase the counter by 1 here. And if it's not true, I'm going to increase the counter of box 0, of how many times it took 0. Why would I increase the array of 0 boxes? It will never take 0. So if I ever see anything in that entry, I know that must have been, it exceeded that. Otherwise, I can't tell if the difference of, maybe it was 2 times num prizes squared plus 1 versus 2 times num prizes to the 4th. So by putting the extra large ones in the 0th entry of the array, I know that those had to be from something that was long. Okay. Ooh, that seemed to move it backwards. Oh, that's interesting. And so here's the result of running things a few times. 10 prizes with 1,000, I'm sorry, with 100,000, and 10 prizes with 1,000,000. So if you look at this, it's an interesting distribution. It does not look symmetric about the mean. It looks like it definitely has a decent tail. And the question is, does this converge to something nice? Well, it's a discrete process in terms of how many boxes there are. So maybe it converges to something nice as the number of prizes grows, so that it almost looks more like a continuous problem. With t log t as the expected number of boxes I need to open, if the number of prizes is very small, there's only 10, the discreteness could really play a role. If there's 100,000 prizes that are possible, then the difference between t log t and 1 more than that is really insignificant. So the hope is that maybe this converges to something nice, and maybe this is a famous distribution. So there's not that many distributions, fortunately, that seem to arise in probability problems. This is great. This means if we know just a bunch of standard distributions, almost surely one of them will model whatever comes up. And a lot of them have very nice computations for their means or their variances or stuff like that. So the question is, does this converge to something nice? This does look like some distributions I'm familiar with. I have some guesses as to what it might be. And there are some famous distributions that are actually special cases of something living in a family of distributions. And we'll talk about that on one of the prospective Frosh days. That's when I will give a lecture on baseball mathematics and talk about how some of the distributions I learned about when I was doing physics actually came to analyze what's going on in Major League Baseball. So again, you see the same stuff in many different places. I did a comparison as to, does it take a lot more time to run if I am storing things in an array? And they were basically about the same amount of time, 131 seconds versus 136 seconds. I think that's within fluctuations of just my computer running. It is doing a little bit more work to store things in an array, but not a significant amount. So I wouldn't be surprised if the array took slightly longer, but it shouldn't be taking too much longer in terms of what's going on. Okay, So that's all I wanted to really say about coding. The differentiating identities at the high level, I'm doing it right now with sums, but you could do it with integrals. We have some expression, and for our expression, sorry, just dealing with a kid issue. We have it depends on a bunch of parameters, and we sum over n. So when you sum over n, should n be on the right-hand side? No, we've summed it out. It's like if you integrate a function over x, you shouldn't have x on the right-hand side. If I integrate, f of xy dx, x goes from 3 to 13, this should just be some function of y. There should be no x dependence. I've integrated out the x dependence. The hope is if I can evaluate the sum and get something nice, I can now differentiate both sides. And if I differentiate both sides, I will hopefully have something nice on the left equals something nice on the right. And the left-hand side is often the quantity I want to understand, and the right-hand side becomes a way to get it. This is an incredibly powerful technique. It doesn't work if I don't know an identity to start things off. I need to know that this sum is equal to some function g. Okay. So now we have a whole slew of things we can do. We need to start with identities. So let's look at the binomial. So the binomial theorem, x plus y to the n is the sum, and goes from, k goes from 0 to n of n choose k, x to the k, y to the n minus k. If we let x equal p and y equal 1 minus p, this is the binomial distribution with parameters n and p. And then the term n choose k, p to the k, 1 minus p to the n minus k, is the probability of exactly k heads with n tosses independent of a coin with probability p of heads. Right? And we showed, so here, x is equal to the number of heads in n independent tosses. So x is binomial NP, but x was also equal to x1 plus xn, where each xk was Bernoulli p. And so we used linearity of expectation to calculate the expected value of x. Since they're independent, could we calculate the variance of x? Absolutely. And I made sure I put a slide just so that it's in the notes. Let's use the binomial theorem. Okay, so now we're going to solve with differentiating identities. So we want to compute the sum, k goes from 0 to n, of k times the probability x equals k. So we need to study the sum, k goes from 0 to n, of k times n choose k, p to the k, 1 minus p to the n minus k. So when we're trying to compute this, maybe we should write n choose k as n factorial over k, k minus 1 factorial, n minus k factorial, because maybe the k will cancel one of the factors in the denominator, and maybe we can play some games. This seems like a natural thing to try. I've got a k, and I know with the n choose k, I have a k in the denominator. Maybe they cancel. Maybe there's a way to rewrite this in terms of binomials. If I were to do that, because I now have a k minus 1, the sum of the terms in the denominator equals n minus 1. So maybe I would pull out an n, and then maybe in the p to the k, maybe I'd pull out a p, and maybe there's some algebra games I can play. I've been doing this long enough that I would give myself a decent chance of being able to do this. I don't like those odds. If I give you the following deal, you can get an A+ for all your classes at Williams if you can find the roots of a quadratic. Yes or no? Why? What will you do? Yeah. What would you do? Quadratic formula. Does it matter how bad the coefficients are? If I give you a nice quadratic, say x, let's see if you can do this in your head, x squared minus 7x plus 12. Can you factor this in your head? So,
minus 4x minus 3.
Okay, I was thinking x minus 3x minus 4, but I'll accept that. So you did the quadratic formula in your head and you simplified it? Or did you just look for, well, I got to have things that multiply to 12, and they've got to sum to -7. So for something like that, sometimes when you have a problem, it's best to just see, can I divinely inspire myself to a good, quick solution? And if that works, wonderful, I'm done. If that doesn't work, then you roll up your sleeves and say, okay, well, I have this brute force computational approach that I know will work. I'll do that. And so if I can just look at the factorization and see it, great. If not, I'll resort to the quadratic formula. Here, I might be able to do the algebra, but that's going to be work, and I'm not sure if it can work. If I can use differentiating identities and just churn things out, that's a lot better. And so what we're going to do is we know that the sum k goes from 0 to n of n choose k, x to the k, y to the n minus k equals x plus y to the n. What I wanted to have is something close to this. I want to have k times n choose k, p to the k, 1 minus p to the n minus k. How could I get a factor of k from this? What could I do to get a factor of k? So you're looking at this. I need to bring down a factor of k, then set x equal to p, y equal to 1 minus p. How could I bring down a factor of k? What could I do? Differentiate. So we have more than one variable, so it's not enough to say differentiate. So differentiate with respect to, so we take the derivative with respect to x. But if we take the derivative with respect to x, then the power of x becomes k minus 1. What power do we want it to be? So after we differentiate with respect to x, what should we do? How can we bump up the power by 1? Multiply by x. So we apply the operator x d by dx. And when we do that, we'll now get the sum, k goes from 0 to n, of n choose k, k x to the k, y to the n minus k. And now set x equal to p, y equal to 1 minus p, and this becomes the sum, k goes from 0 to n, of k times n choose k, p to the k, 1 minus p to the n minus k. Now, we only did half the problem. What's the derivative of x plus y to the n? When we take the derivative with respect to x, that's just going to be n x plus y to the n minus 1, and then we multiply it by x. And so this is then going to equal n p plus 1 minus p to the n minus 1 times p. Okay, p plus 1 minus p to any power is going to be very nice to compute. That's just 1. And so you just get n times p. We've now calculated the expected value of a binomial random variable. And this is perfectly justified because it's a finite sum. Because it's a finite sum, I can just interchange the derivative and the sum. If it's infinite, I have to be careful. But for finite sum, I can justify this. If I want the variance, do x d by dx of x d by dx of our expression. And then that will give us the expected value of x squared when x equals p, y equals 1 minus p. So this gave us the first moment. If I do the x d by dx again, I'm going to get another k coming down. So let's just do this for completeness. So we have the sum, k goes from 0 to n of k, n choose k, x to the k, y to the n minus k was n, x plus y to the n minus 1 times x. Now we have to take the derivative, right? What operator should I apply? Let's apply the operator x d by dx to both sides. So now we get the sum, k goes from 0 to n. You can see how nice it is by applying x d by dx, we keep the power of x the same. And so now we'll get a k squared, n choose k, x to the k, y to the n minus k. How do we do the right-hand side? So how would we handle the right-hand side? We have to apply x d by dx to both sides. How do we calculate the derivative of the right-hand side? So this is a calculus question. What rule do we use? Product rule. So this is the same as x d by dx. So we first take the derivative of the first one. So it's going to be n minus 1, x plus y to the n minus 2 times x, plus n, x plus y to the n minus 1 times 1. Right? And then we set x equal p, y equal 1 minus p. And I'll leave that for you to continue. So the product rule wasn't too bad. And now we've calculated the second moment. So a lot of times as you go further in mathematics, so much of it comes down to what is the easiest quantity to look at. So because we were doing x by dx, we were getting the pure moments. If I just did d by dx, I would get something a little bit different. And so you have to look at each problem to see what's best. There is a way to take the derivative of the right-hand side without using the product rule. So I will just put this in as fun. Avoiding product rule. X plus y to the n minus 1. Oh, can I ignore the n outside? This is the same as x plus y minus y. So you need to learn how to do nothing. There are two main ways to do nothing. You can add 0 and you can multiply by 1. If I do it like this, notice this is now just x plus y to the n minus x plus y to the n minus 1 times y. These are going to be very easy derivatives to do. I don't have to use the product rule. So I can actually bypass the product rule by writing it like this. You'll get the same answer. Bless you. So this is a very nice way to calculate all the moments of a binomial random variable. And now we can keep playing the games. What's another random variable we should look at? There's a couple of natural candidates. What are our favorite random variables to look at? Normal, okay? Normally people would have said exponential before normal, but you want to give me a challenge, fine, give me a challenge. All right. Normal random variable. So the density is 1 over square root of 2 pi sigma squared e to the negative x minus mu squared over 2 sigma squared. Did we do in class that this integrates to 1? Did we do the polar trick by squaring things? We did that, right? Yes? I've seen it. I'm sorry?
I don't remember, but I think not probably.
I saw at least one person nod their head that we did do this in this class. Okay, so we will assume that we know this. The way you write this is, without loss of generality, do for mu equals 0, sigma equals 1, and then change variables. And you can write the integral from minus infinity to infinity of 1 over square root of 2 pi e to the negative x squared over 2, integral minus infinity to infinity 1 over square root of 2 pi e to the minus y squared over 2 is the double integral of 1 over 2 pi e to the negative x squared plus y squared over 2 dx dy. I guess this should be y. And then you write this as the integral of 1 over 2 pi e to the minus r squared over 2 r dr d theta. R goes from 0 to infinity. Theta goes from 0 to 2 pi. The theta integral is going to be very easy. The theta integral just gives you 2 pi because there's no theta dependence. The r integral, oh, we must live well, right? We have e to the minus r squared over 2. What's the derivative of r squared over 2? It's just r. We have r dr. So the minus sign means we switch the order of integration, and we will get e to the minus r squared over 2 at 0 and infinity. At 0, we get 1. At infinity, we get 0. And so this is equal to 1. And so this proves that it does integrate to 1. So this is the special case when the mean is 0 and the variance is 1. If the mean is not 0, that's just translating it. So you can just replace x with x minus mu. It's not going to change anything. The next one is a little bit harder. It's rescaling. And when we rescale, you have to do a little bit of work. But again, you should be comfortable at this point. This is a 300 level math start class in rescaling your variables so that you can adjust for the sigma. If you have trouble with that, talk to the TAs, talk to me. Okay, so let's try to calculate the moments. All right, so we know the integral from minus infinity to infinity of 1 over the square root of 2 pi e to the negative x minus mu squared over 2 sigma squared dx equals sigma. I just took the sigma squared that was in the denominator underneath the square root sign on the left, and I moved it to the right. Is everybody comfortable with my just taking the sigma squared underneath the square root sign on the left and moving it to the right? We're good with that? Okay. What should we differentiate both sides with respect to? I'm sorry? There's no r here. We integrate the left-hand side with x, so x is gone. What's the only things that are left? What parameters do we have that are left? Mu and sigma. You got a 50-50 chance. What should we differentiate with respect to? Whatever we do to one side, we have to do to the other. Sigma, right? If we differentiate with respect to mu, it's going to just be 0. Let's differentiate with respect to sigma. I moved sigma over, so I now have an equality involving sigma on both sides, and I don't have to use a quotient rule. I could have kept everything here. The derivative would have been 0. I could have done the quotient rule. The algebra would have been much worse. It's much nicer to do it like this. So let's apply d by d sigma. And maybe I will want to multiply by a power of sigma. I'll keep that option open. Okay. And so I'll multiply by sigma to the a, where I don't know what a is yet. So I will get the integral from minus infinity to infinity, sigma to the a, 1 over the square root of 2 pi. And now I've got to take the derivative of the exponential of x minus mu squared over 2 sigma squared. What rule do I use to take the derivative of that? Chain rule. As soon as you hear the word of, it's chain rule. I have the exponential of crap. Ah, it's the chain rule. So by the chain rule, it's going to be e to the minus x minus mu squared over 2 sigma squared times the derivative of x minus mu, and I'm going to write it this way. X minus mu squared over 2 sigma to the minus 2 dx equals, what's the derivative of sigma with respect to sigma? 1. So I'll just get sigma to the a. And I'm giving myself a little bit of freedom in terms of what value of a is good. For the previous problem, I wanted to have a p to the k. When I differentiated, I got an x to the k minus 1. The power was 1 smaller. It wasn't that hard for me to look at this and know I need to increase my power by 1 when I differentiate. Let me multiply by x d by dx. For this problem, do you know exactly, looking at this, what power of sigma you're going to want? No, it's a little bit harder. So when you don't know, give yourself a free parameter. I'm giving myself this free parameter a, and then I'll eventually try to figure out what is the best choice of a for this problem. Okay. Who wants to take the derivative with respect to sigma of x minus mu squared over 2 sigma to the minus 2? Is this a product rule, a quotient rule, something else? Is it a quotient rule? No. Is it a product rule? You could do it as a product rule. It's a product of 2 functions. Why wouldn't you do it as a product rule? Yeah, there's no sigma in the first part, right? We are taking the derivative with respect to sigma. We're considering x and mu, they're fixed. If you want, I could maybe use partial derivatives, but x and mu are fixed. Now, I have to justify that I can move the derivative inside the integral. We're not going to be able to do that in this class. That's where you would take an analysis class and they would rigorously show you why this is the case. In brief, the exponential function is nice. The exponential of a negative quadratic is even nicer. It's going to have rapid decay. Everything is fine. All right, so we get the integral from minus infinity to infinity, sigma to the a, 1 over square root of 2 pi, e to the negative x minus mu squared over 2 sigma squared. Then we have x minus mu squared over 2 because, oh, I'm sorry, there's also a minus sign here. Drop the minus sign. Because that's just a constant. Now, what's the derivative of sigma to the minus 2? So it's minus 2 sigma to the minus 3 dx equals sigma to the a. Oh, look at this. The minus signs cancel, the 2's cancel, right? And this is the integral from minus infinity to infinity, e to the negative x minus mu squared over 2 sigma squared. We have a dx, the 2's cancel, we have a sigma to the minus 3, we have a sigma to the a, 1 over the square root of 2 pi, and then, so I have, I think it's 6 minus 2a down below. Yep. Does everybody agree that it's 6 minus 2a below? Sigma to the minus 3, that's 1 over sigma cubed. If I bring it inside the square root, that's going to become a sigma to the 6th. Sigma to the a, that becomes, if I put it in the denominator, it's 1 over sigma to the minus a, but I have to bring inside the square root. What would you like sigma minus 2a to be? Nope. Nope. 2. Why 2? Because that's sigma squared, and then this is the density. Oh, I dropped the x minus mu. Sorry. Integral from minus infinity to infinity. I still have the x minus mu squared. So if sigma minus 2a is equal to, if 6 minus 2a is equal to 2, this is the density of the normal. If 6 minus 2a equals 2, this is the density of the normal. And this whole thing becomes the variance. Okay, so this is sigma to the a, and so this is sigma squared if 6 minus 2a equals 2, as that makes a equal 2. So I wanted to regain the density of the normal. To regain the density of the normal, I need a 1 over square root of 2 pi sigma squared. I had the 1 over square root of 2 pi. I needed the sigma squared inside that down below. And so I just gave myself a little bit of freedom with the sigma to the a and said, what power of a is going to work so that I'm going to get the density of the normal? A equals 2. And now I've calculated the second moment, the second centered moment, x minus mu squared. I've got the variance. Why am I not calculating the first moment of this? Well, I'm assuming you all know that the integral of x minus mu times this is going to just be 0. We've normalized it that way. So if I just look at the integral of x minus mu times that, it's symmetric about that. This will give me x minus mu squared. I can get x minus mu to the 4th. I can get x minus mu to the 6th. So as an exercise, you can now use this to calculate all the moments. Things become a little bit cleaner if you set mu equal to 0 and just translate. And if you think about it, why not? Why not make your life easy and translate it so that the mean is 0? Okay, I will not do this for exams. Okay, but when you're doing a lot of comparisons, it's nice if you adjust things so that the mean is 0. Once the mean is 0, what should you adjust the standard deviation to be? What's a nice value for the standard deviation? 1. So we often call this the standardization of any random variable. If the moments are nice, rescale, translate so that the mean is 0, and then change your units so that the standard deviation is 1. Does anybody know how far the Earth is from the sun on average, approximately? Come on, this is local geometry.
93 million miles.
It's on the order of 90 million miles. Okay, or 1 astronomical unit, where one astronomical unit is defined as the average distance of the Earth from the sun. And so when you want to talk about how far the different planets are, it's often nice to just compare relative to the Earth's orbit. How much further are you? That's a good unit to use. And so if I give you a random variable, we often just care about relative quantity. So if I look at the fourth moment, I don't necessarily care about the fourth moment in isolation. I care about how is that relative to the second moment. If I were to take more derivatives, I could easily calculate the fourth moment of x minus mu. Now, if I took the derivative of this immediately, I would have some trouble because I've got a sigma in the denominator. So what I would do is I would actually clear things so that I would only have sigmas on the right-hand side. If I wanted to have sigmas only on the right-hand side, what would be a good choice of A so that I only have sigmas on the right-hand side? 3. And so if I take A equals 3, then there's only sigmas on the right-hand side, and then I would just have to multiply by an appropriate power of sigma to then have it be the normal density. That's fine. Okay, so this is how you would calculate the moments of the Gaussian. All right, let's do exponential. So the density is 1 over lambda e to the negative x over lambda, 0 less than equal to x, less than equal to, well, I guess I'll just do less than infinity, and 0 otherwise. What do you think the mean is? And we've done this calculation before. What is the mean of this random variable? So what is the mean of an exponential random variable defined this way with parameter lambda? What should the mean depend on? Lambda. So the question is, how does the mean depend on lambda? So we've done this before. It's just lambda. This is why I like to define my exponential random variable like this. There are other people who do it, w e to the minus wx or omega x. And then in that case, the mean is 1 over w. There are advantages. You don't have the division by lambda. I'll take the division by lambda. Okay. So if we want to calculate the mean, that's the expected value of x. That's the integral from 0 to infinity of x 1 over lambda e to the minus x over lambda dx. How would you calculate this? What technique would you use? So we have to do this integral. How would we do this integral? You don't know that many integration techniques. It's integration by parts. So you have, usually there's an obvious choice. Do you want u to be x, so when you take the derivative it gets smaller? Or do you want dv to be x, so when you integrate the power of x becomes larger? I think we want u to be x, right? And then du would just become dx. dv is e to the negative x over lambda dx over lambda. And then what's function has this as its derivative? Negative e to the negative x over lambda. And so integration by parts plus u, it's going to be uv at 0 infinity minus the integral from 0 to infinity of v du. And if it's been a while since you've done stuff like this, it's not a bad idea to just put in all the steps. And notice I have everything here, so it's just now plug in and simplify. The more steps you do, the less likely it is that you're going to make a mistake. All right, so if I plug things in, I now get x and v is negative e to the minus x over lambda at 0 and infinity. The negative and a negative is a positive. Integrate from 0 to infinity v du. That's going to be e to the negative x over lambda dx. Okay, when x equals 0, x e to the negative x over lambda is 0. When x equals infinity, well, the x is going to infinity, but the exponential is going to infinity a lot faster. E to the negative x over lambda is going to be going to 0 very rapidly. So this term is going to be 0. If you are unsure about this, you could do L'Hopital. And you could look at x over e to the x over lambda. And if you want, take the limit as x goes to infinity. L'Hopital's rule says that if you have 0 over 0 or infinity over infinity, take the derivative. And this is then the same as the limit as x goes to infinity of 1 over lambda e to the x over lambda, which is just 0. So the boundary term is just going to be 0. So the exponential decays far faster. If you don't like this, another way to see the limit is x over e to the negative, x over e to the x over lambda is less than or equal to x over lambda squared 1 over 2 factorial, where I take just one term in the exponential. If I look at the series expansion for the exponential, if I take just one term, because everything is positive, I've made the denominator smaller, which makes the fraction larger. And that's enough to show that this is going to go to 0. So if you don't want to use L'Hopital, you can actually do it more elementarily. The whole point is the boundary terms vanish. And now we're left with the integral of e to the negative x over lambda. Okay, well, this is just going to be e to the negative x over lambda times lambda, because when you take the derivative of that, and then there's going to be a minus sign, 0 and infinity, and then you will be left with just lambda. So this is a calculation of the mean. And again, if it's been a while since you've done integration, urge you to do this. Do you think you could calculate the integral of x squared times the density? Do you think you could calculate the second moment? So if I gave you the expected value of x squared, so the integral from 0 to infinity of x squared, 1 over lambda e to the negative x over lambda dx, what method would you use to calculate that? Still integration by parts. How many times would you have to integrate by parts? Twice. The first time you would take the x squared, that would be your u, and then that would go down to 2x dx. As you would have to integrate by parts twice. It's not that bad. You can do it. All right. Let's do this using differentiating identities. So we know the integral from 0 to infinity of 1 over lambda e to the negative x over lambda dx equals 1. What do you think I'm going to differentiate with respect to? So I have, yes. Lambda, there's nothing else. There is literally nothing else in the problem. I've integrated out x, it's gone. If I wanted to, I'm very comfortable with my, oops. Could I use that as a variable? Sure. Doesn't matter. It's a dummy variable. It's a placeholder. I'm integrating it out. I can use, it's not quite a smiley face, maybe an indifferent face, right? Doesn't matter. The only thing left is lambda. So if lambda is the only thing that I have left, I'll go back to the standard. If the only thing left is lambda, I have to be differentiating with respect to lambda. Well, if you look on the left-hand side, if I differentiate with respect to lambda, what rule am I going to have to use to take the derivative? I'm sorry? Not the, there will be a chain rule, but what's the first rule I would have to use to take the derivative of the left-hand side? Not, you could do it as the product rule, but no one would say product. Quotient rule. You can say product rule rather than quotient rule, that's fine. But it's really a quotient rule. You can do it as a product rule with one of the functions is lambda to the -1, that's fine. No one wants to do product rules or quotient rules if you can avoid it. So this suggests, hey, why don't we move lambda over to the other side like we did with the normal distribution? When you do something more than one time, it's now called a technique or a trick, right? It makes things a lot easier. So this is the same as the integral from 0 to infinity, e to the negative x over lambda dx equals lambda. Okay? I don't have to do this, but it just makes the algebra a little bit simpler. Okay, so we want to take the derivative of both sides with respect to lambda. Anything else you might want to do to both sides after you take the derivative with respect to lambda? What might you want to do after you differentiate with respect to lambda? Good. And why a? Because we don't know yet what we want to do. And this just gives us a little bit of flexibility. How many of you have taken real analysis? I haven't taken abstract algebra, so if I ask how many of you have taken abstract algebra, I can't raise my hand for that. I did take real analysis, and I have taught abstract algebra. In real analysis, what you have at times is what's called a 3 epsilon proof, where you break something up into 3 parts, you show each part is less than epsilon over a third, so when you combine them all up, you get that it's less than epsilon. And you do this so that you look skilled. You know, I got my sum to be less than epsilon. No one really cares if it's less than epsilon or less than 2 epsilon or less than 15 epsilon, because you can always just change epsilon. Now let epsilon be epsilon prime over 15, and I've now shown that it's less than epsilon. So what people typically do is they first prove it, and then they change their epsilon, and then they just go back to the beginning and they just run through things with that new epsilon. So it looks like they made those wonderful choices, but they hide the work that they did. Knowing what's coming, we could, of course, just put in the correct value of lambda's power in the beginning, but that's not going to really show you how to tackle problems in general. It's extremely useful to have a free parameter and then just choose it accordingly to make the algebra nice. All right, so now when we do this, we're going to get the integral from 0 to infinity, lambda to the a. Now we take the derivative of e to the negative x over lambda with respect to lambda. So by the chain rule, it's going to be e to the negative x over lambda, and then the derivative with respect to lambda of negative x lambda to the -1 dx. And the right-hand side is just going to be lambda to the a, because I take the derivative with respect to lambda, I get 1, I multiply by lambda to the a. All right, what's the derivative? What rule do I use to handle the derivative of negative x lambda inverse with respect to lambda? It's just the constant rule. I can pull the negative x out. As an aside, if you want to have some fun with a Calc 1 student, find the derivative of x times the natural log of 5. A lot of Calc 1 students will use what rule? Product rule. It's the constant rule. The natural log of 5 is a constant. The other one that's fun to do is find the derivative of the natural log of 2x minus the natural log of x. 0. Why? Log rules. This is the same as the natural log of 2x over x, which is the natural log of 2. So the second one is an example of one of my favorite things in mathematics. I think Henry David Thoreau is the patron saint of mathematics for his wonderful advice, simplify, simplify. Before you start doing a lot of algebra, see if there's a good way to do it. Rather than taking the derivative of each term and then doing the algebra, notice that I can combine them. It's a constant. Now, of course, you could simplify, simplify, simplify to simplify, but I think it loses some of the force, and so I will allow Thoreau to survive with that. When I was at Brown, there was a donor who was a huge fan of Thoreau and had donated a lot of Thoreau's stuff, including his college algebra textbook with Thoreau's markings on it. And so the library actually contacted me, and I got to look at, how Thoreau did the Euclidean algorithm and stuff like that. And so it was interesting to look at this. But you really want to think, what is the best way to simplify calculations? What's the best method to use? There's a lot of methods that will work. And if you get the right answer, that's fine. But the more computationally intense your approach is, the more likely you are to make a mistake. So anything you can do to cut down on the calculations you are going to have to wade through, it's worth it. Take a moment or two to think about the calculation before you proceed. Give yourself some flexibility. All right, so now as we continue, we get the integral from 0 to infinity, lambda to the a. Lambda to the -1 becomes minus lambda to the -2. So the lambdas reinforce. So we'll get x e to the negative x over lambda, lambda to the -2 dx equals lambda to the a. So we have the integral from 0 to infinity of x lambda to the a -2 e to the negative x over lambda equals lambda to the a. What would be a good value of a to take? One, because if you take a equals 1, this is now the density. This is the exponential density. And now this becomes the mean. So the expected value of x is just lambda. That wasn't so bad. And we avoided integration by parts. Now, integration by parts is not horrible. What is your least favorite integration technique? If you don't answer what I'm thinking of, it's because it was so traumatic you forgot you learned it. Least favorite integration technique. Normally, people who remember would say partial fractions. It turns out partial fractions are useful for a variety of things. But notice, we solved this without having to do integration by parts. For the second moment, we would have to do integration by parts twice. Let's see if we can get the second moment. So we have the following expression. So we know the integral from 0 to infinity of lambda to the a -2 with an x e to the negative x over lambda dx equals lambda to the a, right? If we want to take more derivatives, what could we do? Do we want to take derivatives as things stand? So we know a equals 3 is pretty good. And so that gives the integral from 0 to infinity of x 1 over lambda e to the negative x over lambda dx equals lambda. What should I do now to both sides? I'm sorry? Or did I take equals? Oh, sorry, equals 1 or 3. Yes, thank you. Yes, thank you. What should I do now? Do I want to take the derivative of both sides with respect to lambda? What should I do before I take the derivative of both sides with respect to lambda?
Also, those are the lambda.
Yeah, move this lambda over. Right? This is the Henry David Thoreau, simplify. I want to put all my lambdas, if I can, that are not in the exponent on the other side to make things easier. So we now have the integral from 0 to infinity of x e to the negative x over lambda dx equals lambda squared. Okay, that's kind of sad that I don't have the probability density function anymore, but I'm only missing the probability density function by a 1 over lambda. I can always get a 1 over lambda just by multiplying by it later. It is worth doing this to make the algebra nicer. Now I can take the derivative. So let's take the derivative. Clearly, it's got to be with respect to lambda. I could give myself a free parameter. Anybody want to be brave enough and guess what we should try? Or should we do a free parameter? Let's be safe and do a free parameter, right? Should we use the same letter A? Or should we use a different letter? Let's use B, right? Notation matters. If I use A, that might mean it's the same A as before. I've already written A equals 1. Well, actually, I wrote A equals 3. You corrected me to A equals 1. Better to use a new variable. Let's use B. So now if I take the derivative with respect to lambda and multiply by B, I'll get the integral from 0 to infinity, lambda to the B, x. And now I'll have e to the negative x over lambda, d by d lambda of negative x lambda inverse dx equals, what's the derivative of lambda squared with respect to lambda? So I'll get lambda to the b times 2 lambda. So I get the integral from 0 to infinity of x lambda to the b e to the negative x over lambda. The derivative of negative x lambda inverse, then I'm going to get negative x minus 1 lambda to the minus 2. The minus is reinforced, and I'll get b minus 2 dx equals 2 lambda to the b plus 1. What would be a good choice for b? We take b equals 1 and we get the exponential distribution. So this, oh, sorry. This is x squared because we now have 2 x's. So this is now the expected value of x squared. And the right-hand side is just b equals 1 is just 2 lambda squared. So the variance of x is the expected value of x squared minus the square of the expected value of x. 2 lambda squared minus lambda squared is lambda squared. We just calculated the variance without doing 2 integration by parts. So again, whenever you see a technique, you always want to ask, is this worth it? I think this is worth it. These are much easier calculations to do. As an exercise now, you could try to see if you can calculate a general moment. Whenever possible, if you have an expression you want to see, is the answer reasonable? So what we've shown so far is, let's say x is exponential, is exponential with parameter lambda. So the density is 1 over lambda e to the negative x over lambda. We've shown the mean is lambda, the variance is lambda squared, the standard deviation is lambda. If you think about things in terms of units, if lambda is in meters, x should be in meters. And x over lambda, that's a unitless quantity. Okay, that's good. I should not be exponentiating something that has dimensions. So the standard deviation should have the same units as the mean. The variance should have the square of the units. Units work. If this is meters, this is meters squared, this is meters. Units work. It's a little bit interesting that the exponential, that the standard deviation is the same as the mean. But I would view this as, I'm not sure. Should you view it as you're dividing by the mean or you're dividing by the standard deviation? What's the right way to view this? Is it x over the mean or x over the standard deviation in the argument? In the normal, it was x minus mean squared over standard deviation squared. It's sometimes hard to figure out what's the right way to look at things. You know, when I look at that lambda, is that lambda in the denominator, is that the mean or is that the standard deviation? Okay. I want to do a quick aside about the dangers of interchange. So what I'm going to do is I'm going to consider an infinite grid in the upper right quadrant. Because we don't have too much time, I won't draw an infinite grid, although I might be able to. Yeah, I can at least get a bunch of them pretty quickly. That's actually nice. Not a few more. And it goes off to infinity. So this is the point 0, 0, 1, 0, 2, 0, 3, 0, and so on. This is the point 0, 1, 1, 1, 2, 1, 3, 1, and so on. And I want to show that if I consider the infinite sum and I do them in different orders, so in one I do the horizontal sum first and then the vertical, and in the other I do the vertical and then the horizontal, these are not the same. And here's how I'm going to define my sequence. It's going to be +1, -1, and then 0 for the rest of eternity. Then it's going to be 0, +1, -1, and then 0 for the rest of eternity. Then it's going to be 0, 0, 0, +1, -1, 0 for all eternity. 0, 0, 0. Wait a minute. I think I put them in the wrong spot here. Sorry. Sorry. +1, -1, 0 for all eternity. +1, -1, 0 for all eternity. 0, 0, 0, 0, +1, -1, etc. What is every vertical sum? So if I do vertical, then horizontal, what do I get? So each vertical sum is 0. So if I do all the so if I do any vertical sum, it's 0, and then I sum over all the verticals, I get 0. What if I do horizontal, then vertical? 1. Every horizontal row is 0, except for the first, which is 1. This is the simplest example I know where it matters which order you sum. You can't just change the order. So in Calc 3, you should have seen Fubini's theorem. When can you switch the orders of integration? And if the integral of the absolute value is finite, then you can switch. If I put in absolute value signs, this explodes. You have to be careful. I'll do one last example. Here is 2 over n, 1 over n, 3 over n. And I'm going to define a function, here's 0, as follows. Fn of x is 0 if x is less than 1 over n or x is greater than 1 over n, 3 over n. And it's the triangle with height n otherwise. All right, so everybody understand? I have a triangle of height n centered at 2 over n. What's the integral from 0 to infinity of fn of x dx? So for any n, I've got a triangle of base 2 over n and height n. What's the integral? It's just 1, right? So the limit of the integral of fn of x dx, what would that limit be? If it's always 1, what's the limit? 1. But the limit as n goes to infinity of fn of x is 0 for any x. If x is 0, it's always 0. Otherwise, just choose n so large that 3 over n is less than x. So the integral from 0 to infinity of the limit as n goes to infinity of fn of x dx equals 0. The limit of the integral is not the integral of the limit. This is not a class with real analysis as a prereq. This is just 2 quick examples to show you we have to be careful. And just because things are working doesn't mean that they will always work. All right, so that's all I wanted to do from that. All right, so this is a good place to stop.